I've changed my topic a little bit from what's written there because I wanted to speak a little bit more broadly than just about heavy metals. Because this is the year of the element, and I think one thing that we need to remember, heavy metals are problems, but I can tell you, and I will show you today, that carbon is a terrific problem. Okay, there's our chemical sciences building at UWC, and this is my research group. I've got about 30 students in the research group doing all kinds of different things, and the work that I'm presenting today comes from their MScs and PhDs. So we're actually a material science group, which sometimes confuses people, and we apply the materials in water or in waste or in catalysis or in separations. I'm going to focus mainly on water and waste today, but there are other things that we're busy with that are quite interesting in terms of material science development. So as you know, worldwide, water is seen as one of the most problematic issues. We've got a very high impact from water problems and a very high probability. So it's considered to be one of the most critical issues in the world these days. Now, you might not know it, but water in the industrialized world is highly contaminated. And this is where I'm going to talk to you about the element carbon. In Africa, we have a huge problem with microbes. It's also a form of carbon. As we heard earlier on, living beings are mainly made of water and carbon and nitrogen. Hey? Microbes are also made of carbon. So please don't forget the microbes, but I'm not a microbiologist, so I'll leave it to the people that do microbiology to talk about it in detail. I'll just skim over the microbiology. But please remember that microbial pollution is still one of the most problematic things in Africa, and certainly in South Africa we're nowhere near to solving the microbial pollution issues, as we saw with the Vaal and the sewage, and we'll come back to the sewage because it's not just microbes in the sewage. So if we have a look at South Africa, as you can see from that graphic, our water availability is slowly but surely putting us into the very critical position, because we actually are starting to run out of water resources. Now, that is due to climate change, and it's also due to population growth. Here you can see a map of South Africa showing you the available water sources, and also the possibility to actually increase our storage capacity or our water harvesting capacity. And you can see that in many areas we're already using more water than what is available, and there's just about no extra capacity in the country to produce more water. So water is a boundary condition. Have you heard of a boundary condition? It limits growth. So unless we start reusing our water and using our water much more smartly and thinking of it as a cycle, we're going to end up in a real pickle in this country if we're not already in one. I was just in Makanda last week, also on a NSTF presentation, and you know yourselves that town has been completely without water for quite a while. And I lived through the whole drought in Cape Town, so let me tell you, it's not so comfortable to try and get by with 50 litres of water a day. Now here you can see why I say water is a boundary condition. If you look where our population was in let's just get that right, that's around about 1960, we were under 20 million people in the country. Please put your head around that. Under 20 million people in the country in 1960. We're now heading to 57 million people. So our population is doubling on average every sort of 20, 30 years. However, our infrastructure has not kept pace with the growth in the numbers in the country. And these are not immigrants, these are South Africans having lots of children. Unfortunately, it has to be said. Nobody wants to say it, but we have to say it. And if we're going to have so many people, we need to start planning. We need to start thinking about where we're going in the future. Now here you see how climate change is busy changing issues in South Africa. You can see from around about 1979, we've basically gone into a much warmer temperature. And there have only been a few years since 1979 that we've actually been below the average. Our temperatures are just going up and up. And that means that our climates are becoming drier, and the water availability that we used to rely on is actually shrinking. Here you can see a rainfall and seasonal variability across the country, and you all know that we've been in periodic droughts. Now, in my lifetime, and for those of you who are my age, you will know that we've been through about 5 or 6 drought cycles, and some of them were severe, but the latest lot of drought cycles have been actually worse than before. The other thing that we must never forget is that our spatial variability of water in South Africa is quite skewed. We have a very large water availability on the Natal and Mozambique coast, but down in the middle of the country and towards Cape Town, we have a much drier climate. So, having got that in your head as a background, let's have a look at what's in our water. Now, we need to realize that there are viruses and microbes and parasites that are living organisms that are in our water and that can cause disease. What I mean with that is they can make you ill from a disease. So it's not because of bioaccumulation, it's not because of toxicity, it's because of a disease process, it's a pathology. So if you have bilharzia in the water and you go and play in that water or you drink that water, you will get bilharzia, which is a disease. If you drink contaminated water and there's E. coli in that water and other enteric organisms, you will get gastroenteritis. So that's one thing about the water. The other thing to remember is that we always measure the physical parameters of water, and that has got to do with its pH, and it's got to do with its electrical conductivity, and it's got to do with its total dissolved solids. Those are physical parameters. And those physical parameters are what they are because of the chemical parameters. Now, the chemical parameters get divided into inorganic and organic compounds. Now, inorganic means everything on the periodic table except carbon. And organic means carbon. Now, that's why I want to say carbon is a hugely problematic element, and we've completely overlooked carbon while we've looked at all the other elements on the periodic table and the problems that they cause. So let's have a look at carbon's problems. Carbon is basically what is in sewage. And we all know that across our country, we have malfunctioning wastewater treatment plants, and not only so, we don't have sufficient wastewater treatment plants because we haven't been thinking about the population growth. We have to build new infrastructure. We can't just continue trying to patch the old infrastructure. And as you can see, that there are only a very small percentage of our wastewater treatment plants that are actually functioning fairly optimally. So you can see there in the Western Cape, we've got, in the whole country, there are about 10% of our wastewater treatment plants that are functioning properly. So what does that mean? It means that a huge load of microbes, inorganics, and organics are going into our rivers and into our oceans. Now, when I say microbes, I'm differentiating them from organics, which are the solids in sewage, and those solids are not just feces, it's also all the chemicals that you use every day in your daily life. And we'll get back to that just now. Think about your toothpaste, your shampoo, your washing powder, etc., all going into the sewage plant. Okay, now for microbes, we typically test for these organisms because if they're there, the water is contaminated and you can get a disease. our South African standards, the national standards, actually use E. coli or fecal coliforms as indicator organisms. That doesn't mean that those are the only organisms there. It means that those indicate that there might be pathogens there. Because if there's feces in the water, you're likely to have pathogens there that can make you ill, give you a disease. Now, if we look at our groundwater across the country, our groundwater is heavily salt-laden. So here we're talking about the inorganic salts. So if you have a look at the purple areas and the green areas on this map, those are areas where the water is actually saline. And we have a problem getting salt out of water. There are areas in our country where the groundwater is sweet or lacking in salt, but that lack is not a bad lack, it's a good lack. Okay, the trouble also is with our planning is that we're planning to do the fracking across the area where we have our water reserves. And I showed you earlier on that a lot of our water is actually our water supply comes from groundwater. And fracking is notoriously bad at damaging our water supply. And the anions and cations that we find in those very salty waters are some of these compounds, which are elements such as nitrate, sulfate, fluoride, ammonia, chloride, and sodium. I mentioned the physical parameters earlier on. I'm not going to spend a lot of time on that, but that is usually the quickest way to check whether your water is actually contaminated or not. Inorganics, the whole periodic table is in our water to a different extent. It depends where you are and what has been happening to your water. But these are typically the type of elements that one would worry about in your water. And if you have a look at coal mine drainages, sulfates are a huge problem with them. And the sulfates actually also are going together with a very low pH. So the water is like vinegar or even more acidic than vinegar. And this is a widespread problem everywhere where we're busy mining in pyrite-bearing rock, as our previous speaker spoke about, the fact that sulfate actually is a problem in some of the soils. Here is a very busy slide, but the take-home message is this is the sort of elemental contamination at a gold mine in South Africa. And the take-home message of this is the amount of uranium that is in that water in terms of its activity. So here you can see that you have a very high activity in terms of its becquerels per liter in some of the gold mine waters. And I can tell you we've also tested the gold mine waters, and they've also got a fairly high becquerel activity. Now, why is that a problem? Because of radioactivity. Radioactivity causes all kinds of genetic problems and other kind of problems, and cancers, and it will kill off your thyroid and all kinds of other diseases that are not caused by a microbe, but caused by exposure to the radioactivity from this water, and from mine dumps, might I add. Here you can see how the uranium is distributed in terms of its species in mine water. Suffice to say that it stays in solution quite well. So it is transported very large distances, and anywhere where that mine water is busy decanting or flowing, it is busy contaminating your sediments and your soils with uranium. Okay, now mine water can be treated in a whole variety of ways, and I'm not going to go in detail with these treatment options. The problem is not that we don't have treatment options. The problem is that people don't want to apply these treatment options for various reasons, and therefore the water doesn't get cleaned up. One of our big problems is that we can't get mine closure because of the amount of sulfate in the water and the heavy metals in the water. And it's basically because a lot of these processes are too expensive to carry on using in perpetuity, because when you start a mine in a pyrite-bearing rock, you are looking at a problem that is going to last for thousands of years until all the pyrite is used up. That mine will carry on producing acid mine drainage. The only way to stop acid mine drainage is to close the hole and stop oxygen getting in there. Then you stop the weathering process, and then you stop producing sulfate. So we have to start looking not only at closure of mines, but closure of the voids. Now, the way we want to approach that is by this last process here, which I call the Petrik's process. We patented it in around about 2000 and, we invented it in about 2003, and we got it patented in about 2006. And in that process, we're using the very large waste called fly ash that remains after you've burnt coal, and we're mixing that with the acid mine drainage. And in that process, we're actually dropping out almost all the metals and sulfates out of the water. And the interesting thing about that is that there's no membrane process involved in there. It's purely a supersaturation mechanism, a redox mechanism, and an adsorption mechanism. And that process is available to mines, and it will be a useful process because it actually produces a residue that is earth-like or soil-like that can be put back into the mine, because the ash from coal comes out of the same place as where you're going to be putting it back, just minus the carbon, the coal part of it. So you fill the void, and you stop the ingress of water and oxygen, and you stop your acid mine drainage forming. So that's what is called a cradle-to-cradle solution for water treatment. Okay, and here's just some of the results to show you how far we get into the cleaner water. And you can see, looking at the sulfates there, with this particular one that we did, we started with sulfates of about 5,680, and after, not even 60 minutes, we had the sulfates down to below 100. So that shows you what you can do with fly ash. And many of the other elements came down too. So these are the trace elements that remain after that process. These are just a few of them, but you can see most of them are under 1 milligram per liter. We also developed a process where we could take the iron out of fly ash, and we made nano iron out of it. So that is using a waste to make a product. And that product we also use to clean water. And here you can see the type of elements that the nano iron could take out of the water. That's a redox reaction, and you're causing the metals to precipitate. But you can see sulfates came out, and a whole host of other metals. And uranium is there amongst all of that, if you can see it. It's round about number 7 or 8 along that list. So we were getting most of the uranium out in that process. Okay, so typically conventional treatments are used for taking inorganics and microbes out of the water, and we usually use reverse osmosis as the final polishing step, but there's usually a process where you have coagulation, adsorption, filtration, ion exchange, and biological processes. So those are designed to treat sewage, and in some cases mine water is being treated with reverse osmosis. It's quite an expensive process, and it results in a very high amount of brine that needs to be stored in hazardous ponds. Now here is a typical wastewater treatment scenario, so you can see what a wastewater plant basically is comprised of. You usually have a screen where you're removing the debris, and then you have some form of settlement pond where you get the sand and the grit out, and then you have primary clarification where you basically settle down the sludge, and you have the sludge digested by microbes. And those solids are then usually disposed. The water that you recover from that process is usually going through aeration and clarification, and then disinfection with chlorine. And that's more or less where our water treatment stops, at chlorination. One thing I would like to mention here is that sludge that's coming out there is hugely toxic. And please remember that the sludge from wastewater treatment plants is absolutely not safe to use on agricultural soil. If you're thinking of using the sludge from a sewage plant on agricultural soil, you are creating a huge problem. We were talking a bit earlier about antibiotics and why are antibiotics landing up in the soil. Well, it's because people are putting sewage sludges on the soil, and the sewage sludges are full of antibiotics from the antibiotics that you and I take, or that we feed to our cattle or our chicken. And that's where the antibiotics in the soil come from, and they kill off the microbes, the natural microbes that should be stimulating the soil's replenishment. So when we put those sludges on the soil, not only are we killing off the microbes in the soil, but we're also allowing some of those chemical compounds to translocate into the plants that we're busy growing on that soil. And it's very well known already that the persistent contaminants, the organic persistent contaminants, translocate into your food. So it's not just cadmium and lead that we should be worrying about. We really need to start looking at the translocation of persistent contaminants, and I'll speak about that a little bit more. That element carbon, remember that element of carbon. So